So you'd like to take advantage of embedded Linux for a vast number of reasons, including lower cost, easier software integration, security and networking capabilities, along with its ability to run on a wide range of microprocessors. But you've heard that Linux can take a long time to boot, and your customers' expectations are to have their product up and running quickly. In this video, we will describe techniques you can use to minimize the boot time of an embedded Linux system. For the purposes of this exercise, we will use the SAM9X60EK development board and the high-performance WVGA LCD display module with Max Touch technology. First, let's take a look at the typical Linux boot process. There are three major steps in booting Linux on Microchip application processors: the bootloaders, the Linux kernel, and the Linux application. Microchip application processors, like most application processors, boot in stages. The first stage of the boot process starts with the embedded ROM bootloader, or boot ROM, inside the processor itself. Its main purpose is to locate the second stage bootloader in the external, non-volatile memory and copy it into internal SRAM. The second stage bootloader then initializes the clocks and external DRAM and loads the next stage. The next stage can be a third stage bootloader like U-boot or the Linux kernel itself. The last stage runs the target Linux application. Now, let's see what steps we can take to drastically reduce boot time. In the first level bootloader, switching the slow clock source to the internal oscillator shaves off almost 1 second. By eliminating the settling time required by the external crystal, which is selected by default. Next, disabling all debug and log messages reduces boot time significantly. The AT91 bootstrap is capable of loading the kernel directly, removing U-boot from the boot process. Employing this technique is crucial for fast boot. Finally, the Linux kernel can be compacted to reducing the overall boot time. The Linux kernel startup time can be minimized by configuring only the necessary peripherals and subsystems required by the application. In this demo, we disabled all the peripherals that are not going to be used by the final application from the SAM9X60 default device tree and kernel configuration. The fewer subsystems and drivers the kernel must initialize, the faster it will boot. Then we added the PDA5 overlay. The PDA5 overlay enables the LCD display. In a typical boot process, the Linux kernel loads the standard init script that loads other services and applications. To minimize boot time, we replace the standard init script with a minimal script that simply mounts sysfs and loads the final application. Sysfs is needed to control the backlight brightness from within the application. The final application is a basic automotive dashboard graphical display, developed with the Ensemble Graphics Toolkit, or EGT for short. EGT is an open-source graphical toolkit developed by Microchip and distributed free of charge. The application is compiled as a static executable. All the images, logos, and resources are compiled directly into the application and statically linked to it. Therefore, there's no time wasted looking for resources in the file system and mapping them into the application's address space. And now for the demo. As you can see from the video, we have an embedded Linux graphical application up and running less than 3 seconds after power up. To learn how to create this demo image yourself, please click on the link in the description. We hope you enjoyed this video. For more information about EGT or embedded Linux on Microchip application processors, contact your local Microchip sales representative or visit our website. Thanks for watching.